In this video, we're going to approximate the largest Lyapunov exponent of the original Lorentz system here in NumPy using the RK4 simulator that we coded in a previous video and by employing a very simple perturbation approach. For this, we will first discuss the strategy of how to do so. Then we're going to code it up with the aforementioned RK4 simulator. We will then plot how the distance between a perturbed trajectory and the original trajectory grows exponentially over time, and how this allows us to derive the Lyapunov exponent using a simple polynomial fit. We will then compare it against a value from the literature and discuss what it means to use the Lyapunov time as a timescale for a system, and what are some rule of thumbs, what that means with regards to predictability. Let's get started. The channel sponsor Perturb is currently hiring SciML and software engineering positions. Check out perturbs.ai/careers for more details. Hi and welcome to this new video where we will again look at the Lorentz system, which is this prototypical example of deterministic chaos. In the previous videos, we implemented simulators using the RK4 method to solve this system of three nonlinear ordinary differential equations. And this then gave rise to this wonderful butterfly shape, which is the form of its chaotic attractor. In this video, we want to quantify what it means to be sensitive on the initial condition. And one popular measure for doing so is the Lyapunov exponent that describes how an ever so small perturbation in the initial condition is growing over time. For this, we will combine the three variables, or correspondingly to the three ordinary differential equations, into our state vector u, which is three-dimensional, and then assume we have an initial condition, u0, as well as another initial condition, which is ever so slightly next to it, for instance, in terms of a measurement or a rounding error. Then we know that its difference, or the difference state, will just be the difference between the two. And if we compute the norm over the difference state, and see how that one develops over time, that one can be approximated in that the initial difference will grow exponentially and uses the Lyapunov exponent, or the largest Lyapunov exponent, lambda, in its exponential. And this one we want to approximate, and it then gives us a feeling of how fast it separates from another. And this then we will ultimately be able to use as a timescale and to make some statements about the Lorentz system. Okay, how are we going to do this? We will again use the default configuration from the original Lorentz paper. So in there we set the three constitutive parameters, sigma, rho, and beta. We will again use the RK4 simulator we coded up in a previous video, again with the same time step size of 0.01. And then we have this multiple approaches actually to compute the Lyapunov exponent. I would say one of the most intuitive ones is a perturbation approach, and this one works as follows. So we will start with a reasonable initial condition, now called u upper index 0, because we're now in this discrete time stepping scheme with a fixed time step width. And we're going to evolve that one. So, for instance, assume we start at 1, 1, 1, or another reasonable initial condition. Then we will evolve this initial condition until it enters the chaotic attractor. So here we do just exhaustively 5,000 time steps, because then we are on this butterfly shape. Then we're going to reset the initial condition to that state after 5,000 time steps, and consider this as a warmed up initial state, because we're sure it's going to be on the chaotic attractor. And then we're going to perturb it with a very small amount. So here we're going to use a noise that is drawn from a uniform distribution from -1 to 1, and then multiply it with a very small number, here 10 to the -8, such that we get a very small perturbation. And ultimately, we're then evolving both the unperturbed state, the u0, as well as the u tilde 0 over time, let's say for instance for another 5,000 steps, and then compute the difference between the two trajectories and compute the norm over all the three state variables. And this then allows us to plot a distance trajectory or how the distance grows over time. And you already saw that in the intro. You will then be able to plot that and can see how that one is growing exponentially linear, which will then allow us to perform a polynomial fit, where we're going to use a data set with the time steps and the data points, where we're also going to apply the logarithm to it. You will see that in a second. And this then allows us to derive the largest Lyapunov exponent lambda, or at least it gives us an approximation of it. Because an optional further step would be that one repeats this process a couple of times and then averages to get a more precise estimate of this Lyapunov exponent. This notebook that I'm going to present, or that we're going to code up, is inspired by an example from the ChapFun library. In case you're not familiar with it, it's definitely worth checking out this library. It's a MATLAB package that has many beautiful examples for any kind of numerical analysis, so it's very cool to check that out. Okay, amazing. Then let's start with the coding. So here I already have an import for NumPy and Matplotlib. We're going to reuse parts of the code that we did for the original RK4 Simulator. For this, we first implemented the right-hand side of the ODE system, and then we implemented the RK4 Simulator in form of an autoregressive time stepper with the call signature basically resolving one time step using a RK4 scheme. Then we can instantiate this one, and we also started with an initial condition. So here, as mentioned before, I will just use a ones or a three-dimensional vector filled with 1. And then essentially what our Lorentz stepper did is that it took a three-dimensional vector and produced another three-dimensional vector, which was essentially the vector further in time. And then we can use this one to autoregressively roll it out. And for this, I implemented a very simple function, which takes an initial condition as well as the number of steps we want to roll it out. And I already hard-coded the 5000 here. So we'll basically just apply the Lorentz stepper and then record the result of it and stack it together into an array. Okay, then let's use this function to produce a trajectory. So we're going to say produce trajectory on U0, which then gives us an array. Let's look at its shape, which has 5001 by 3 entries. It has 5001 because we also include the initial condition. But as I mentioned in the strategy, we start at this 111 vector, and then we do 5,000 steps essentially to only warm it up. So we can then extract the warmed up state. So let's say U0 warmed by indexing the trajectory at the last time step. Then we can add our noise to that. So let's use U0 warmed noise and add our uniform noise to it. So we use U0 warmed plus 1e minus 8 multiply with numpy.random.rand3. This gives us a random three-dimensional vector. By default, it goes from 0 to 1. So basically it's a uniform distribution over 0 to 1, but we can map it to a uniform distribution from -1 to 1 by multiplying it with 2 and subtracting 1. And then we basically have these two new initial states, which we could devolve into a trajectory. But let's first check what is the distance between the two. So we can do numpy.linalg.norm on u warmed noise minus u warmed. And then you see the difference between the two, or the distance between the two, is approximately in the 10 to the minus 8, which fits with the noise that we used to add on the warmed initial condition. Then let's produce both trajectories with an initial condition according to U0 warmed and another one with U0 warmed noise. So let's do U warmed trajectory is produced trajectory applied to U0 warmed, and U warmed noise trajectory is produced trajectory applied to U warmed noise. And now both are 5001 by 3-dimensional arrays. And we're going to compute the distance trajectory. So the distance trajectory, which is using numpy.linalg.norm on the difference. So we're using u warmed noise minus u warmed trajectory. And then we're gonna say we take the norm over axis 1. Axis 1 here means that we have this 2-axis array with the 0th axis being the time snapshots and the first axis being the 3-dimensional state. And we only want to take the norm over the state, because if we do so, we can look at its shape. Then we basically retain a 5001 dimensional vector, which has the distance for each time step. Then let's plot that, and we're gonna plot it in a semi-log y plot. So a plot which is logarithmic on the y-axis and linear on the x-axis, with the distance trajectory, and at an x label which is time step, and then add a y label which is going to be the distance norm. And we will also activate the grid. Here we go. And then we see the following. So here we see the distance trajectory over time, and we will start at approximately 10 to the minus 8, which was the distance we also computed for the 2 initial states. And then if you exclude the oscillations, there is this linear trend. And since we are in a logarithmic linear plot, that is an exponential trend up until a certain point, roughly after 2000 time steps, where it then levels off. So one could interpret it like this, that the distance between the trajectories is growing exponentially up until the point where both are on very opposite points on the chaotic attractor, and then just move around on the chaotic attractor, and we have some sense like the distance or the widest span on the chaotic attractor that's going to be seen here on average. Okay, how do we then use this plot or this information to derive the Lyapunov exponent? So we need to fit a line in here. So we need to make, in other words, we need to make a regression on that. So let's do exactly this. For this, we're gonna prepare an array of time points. So let's say time points, and that one is NumPy.arrange on the length of the distance trajectory multiplied with the Lorentz stepper, sorry, not the Lorentz right-hand side, but the Lorentz stepper.dt. So basically, what does that give us? So arrange will produce an array which is 0, 1, 2, 3, 4, 5, and so on, based on the number we give it here. So the length of the distance trajectory is 5001 because we have 5001 time points. So what does this one give? So we can take a look. If we plot this time points, or if we print it out, we see that the first time point is at 0, the initial condition, and then at 0.01, so 1e minus 2, then 0.02, and so on and so forth, all the way until 50 in, let's say, real physical time. We created this because now we're going to use a polynomial fit routine that is within NumPy, which requires us to present both an X part or an input part of the dataset as well as a Y part of the dataset. And this is going to be our input part because for each of the time points, we know the corresponding distance. And since we want to make the fit in the logarithmic plot, we're going to have our Y data points be the logarithm applied to the distance norm. So there's this very handy function. It's called NumPy polynomial fit. And then what does it require us to hand over? So we need to provide an X and a Y component of the dataset. So the X component, as mentioned, is going to be our time points, the time points. And then the Y component is going to be the distance trajectory. Precisely, it's going to be numpy.log applied to the distance trajectory. And by default, the logarithm is the natural logarithm, so by the basis e, and that's also typically what a basis you use for computing or defining the Lyapunov exponent. And then you also need to provide the degree of the polynomial, and since we want to make a linear affine fit, we put in 1, which computes both the slope and the offset. But now we have to be careful in that we have 2 regimes in the distance norm trajectory. We have this exponentially linear growth regime in the beginning, and then this more or less flat regime after the distance has grown sufficiently. but we're only interested in the initial growth regime. So we're gonna extract the first 2000 time steps. So let's index :2000 to get the first 2000 entries. And similarly, we will do that here. Let's execute that. And then basically it returns us with an array of 2 values. Let's give them some meaning by unpacking the result. Oh, sorry, this one was deleted, but now we can unpack the results. And the first is going to be the Lyapunov exponent, and the second one is going to be the logarithmic offset. And then we can print the Lyapunov exponent, and the result is about 0.934. So this is the slope of the linear curve in this logarithmic linear plot. Or in other words, it's going to be this lambda that is in the exponential. Let's compare this value with one that you can find in the literature. Let me just paste in. So there's a doctoral dissertation which computed the Lyapunov exponent for this particular Lorentz system to be around 0.9056. So our value is a bit off from that, but to be fair, it is also only computed using one perturb trajectory. Of course, you could repeat this with multiple, and then hopefully you will see that the more samples you take, the closer you will get to this particular value. Okay, so now we found an approximation of the Lyapunov exponent, or we could use a value taken from the literature, which are known for many of the chaotic systems that are out there. But what do we do with the Lyapunov exponent? And of particular interest is the inverse of the Lyapunov exponent. I also want to paste in a markdown plot here. You probably already saw that in the intro, in that if you take the inverse of the Lyapunov exponent, you get the Lyapunov time, which is a time scale which you can use to normalize certain trajectories with. But more importantly, many people use it as a measure of the extent of the predictability of the system. Oftentimes they say that after one Lyapunov time, the system becomes chaotic and highly unpredictable, or unpredictable at all. So here, conveniently for the Lorentz system, the largest Lyapunov exponent is around 0.9, so its inverse is roughly at 1.1. So after 1.1 times of physical time, the Lorentz system turns into this chaotic nature or becomes unpredictable. But I guess it's also important to relook at it, what it means precisely. And here, since we use a basis of e, so the natural logarithm, we know that when we have e raised to the 1, this is approximately 2.71. And so if we go all the way up to the definition of the Lyapunov exponent, is that if our time is exactly 1 over lambda, so if we are done 1 Lyapunov time, we have the e raised to the 1, and e raised to the 1 is 2.7-ish. So after this particular time, so after 1 Lyapunov time, our initial perturbation has grown approximately by 2.7. So depending on how large your initial perturbation was, that is still a reasonable perturbation. So I guess it can be interesting to look at what happens if you do multiple Lyapunov times. And there it becomes interesting, and I always find this fascinating because I guess as humans, we have a very bad feeling for exponentials, at least I have, and so it always helps me to have these rule of thumbs. So I already noted this down. If we spend 1 Lyapunov time, so if the time passed is 1 over lambda, the distance is grown by around 2.7, that's what we said. And now if we raise 2.7 to 2.3, we get 10, and this is an interesting part. So if you spend 2.3 Lyapunov times, then the distance has grown by 1 order of magnitude, 1 basically, so by a factor of 10. And then you can basically double that. So if you have 4.6 Lyapunov times, you've grown by a factor of 100. And then if you spend 10 Lyapunov times, and this is now hand wavy a bit, but at least to give you a feeling, then you grew by 4 orders of magnitude. And now if you maybe put this into the context of a measurement error, if you do a small measurement error, how that amplifies over time, and let's say, I don't know what kind of thing you're measuring, but let's say you have a reasonable amount of precision with, let's say, 3 digits of accuracy, 3 digits after the comma or 4 digits after the comma, then this accuracy will be gone after 10 Lyapunov times. And also, if you look at the example we did where we trained the MLP network, the MLP network will make a small error in its very first step. Even if it's like very well trained, it will still make a small error in comparison against the reference simulator. And then this error will also grow over time, inevitably due to the chaotic nature here. But of course, the important insight is that if the initial error that is made is very small, then this means that even after 1 Lyapunov time, the trajectories can still be reasonably close to another. They, of course, will still continue to exponentially diverge, but I guess it's nice to have this context that it does not mean that everything is lost yet after 1 Lyapunov time. Okay, and to maybe also visualize that, let's plot the Lyapunov times into our plot here. So let me first define the true Lyapunov exponent to be 0.9056. And then we will again plot a semi-log y plot on, this time we use also the time points to get the correct time on the x-axis, because in the previous plot the x-axis was time step, but now we want to have it actual time. So we use this array that we created for the polynomial fit. And to really just reduce to this initial phase, I will index up to the thousandths time step, and then also use the distance trajectory up to the thousandths. Let's activate the grid. And then I want to draw some vertical lines at multiple Lyapunov times. So let's do plt.v lines. And the first vertical time I want to have at 2.3 Lyapunov times. So 1 times 2.3 times 1 divided by Lyapunov, true Lyapunov exponent. So basically we have now spent 2.3 Lyapunov times. And then just some vertical limits from 1e minus 9 to 1e minus 3. And then give that the label, or maybe let's leave it without a label. I think that's also fine. And let's also do 2 Lyapunov times, or 2 times 2.3 Lyapunov times, 2 times 2.3 times 1 divided by Lyapunov exponent. Again, from 1e minus 9 to 1e minus 3. And let me just copy paste that. And let's have the same for 3 times that. And let's add the x label of, this time it is time. And again, the y label shall be distance norm. Let's execute that. Here we go. Okay, so basically what we see here is that we have again this oscillatory linear growth, or approximately linear growth in this log linear plot. And then we have here these multiple of 2 times 3 Lyapunov times. So you see, since the Lyapunov exponent is a roughly 0.9, its inverse is roughly 1.1. And if you multiply 1.1 with 2.3, this is roughly maybe 2.5-ish. And that's what you see here. So this could be 2.5, that could be roughly 5, this could be roughly 7.5. And now importantly, if you look here, so in the beginning we start our distance at roughly 10 to the minus 8, and then after 2.3 Lyapunov times, this is grown by approximately an order of magnitude. So if you, let's say, remove the oscillations here, and if we then go further, it's grown by another order of magnitude, approximately, and another one, and so on and so forth. I guess it also helps if we draw in this fitted line. So let's draw that in and say plt.plot on the time points indexed up until 1000, and then essentially we will plot in the linear curve, or precisely the exponential, but which will then appear as a linear curve by saying numpy.exponential on the logarithmic offset plus the Lyapunov exponent. And here it's a bit inconsistent, but now I'm using the fitted Lyapunov exponent just to really see what the polyfit did. and then multiply that one with the time points indexed up until 1000. Okay, let's plot that in as well. And here we go. So basically the orange curve is now the fitted exponential, and you see that the polyfit did a decent job in removing the oscillations and just retaining the linear trend. But now it also should be more visible that here we are a little over 10 to the minus 8, and then here after 2.3 Lyapunov times we are a little over 10 to the minus 7, then a little over 10 to the minus 6. So as I said, each 2.3 Lyapunov times we lose an order of magnitude in the precision, or basically the distance grows by 1 order of magnitude. And that concludes the video. So this is one way to compute the Lyapunov exponent via this perturbation method. In the next video, I want to show you one which is more efficient and also a bit more precise, is to employ automatic differentiation. And for this, we will again swap back to the JAX version of our RK4 Simulator, because JAX supports automatic differentiation, and this is another way to compute the Lyapunov exponent. This channel is supported by Perturb Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed this video. If you did, then please give a like and consider subscribing to the channel. There's more content on nonlinear dynamics, PDEs, and all things related machine learning to this, so I hope you can stick around. Here you will now see similar videos, and I hope to see you in one of the next videos.